sir. Good afternoon. Good afternoon.
Good afternoon, sir.
of dating, marriage, love, romance.
So recording has started. You can give your attendance. So we have ended with this slide where we have discussed what are the criteria by which nature has chosen, say, about 25 elements out of, say, more than 100 elements that are available in nature, and we have enumerated certain criteria here. That means abundance over wide geographical regions of Earth. Then the element chosen must be able to do proper biological function with high degree of efficiency. Then we have said that very important criteria that an element, particularly transition element, which is being chosen for biological function, must have such a property that it forms a thermodynamically stable complex of reasonable degree, but it should not be very stable because then it has got certain disadvantage. And similarly, it has got reasonable degree of kinetic fastness, or what is called lability. So there should be a balance between the thermodynamic stability and kinetic lability, and I have discussed in my last class what happens if there is high degree of stability, very high degree of stability, or very high degree of lability. Then there certain unwanted features come into play. For instance, if we have very high degree of stability, then it may happen that after an enzyme converts a substrate to a product may not be able to dissociate because of the stability of the enzyme product complex. Similarly, I have told you that if a particular metal ion has got high degree of lability, then before the substrate is converted to product, the substrate may undergo dissociation. So we require stability, we require lability, but we require a balance between them. And this balance is obtained in the first transition series, but in the second and third transition series, there is too much stability and too little lability. And as a result of this, second and third transition elements are generally not chosen for biological function. Then we have also said that with evolution, gradually more and more elements are being incorporated, and some elements are also being eliminated from the essential elements. So evolutionary ability to improve specificity and selectivity, and I have given you two or three examples. One example was oxygen, which was not an essential element for the early part of the life living system, but oxygen is now essential. Similarly, molybdenum is now very much essential element, but for early living systems, tungsten was essential, but now more or less for almost all the living systems, tungsten has been replaced by molybdenum. And then final discussion was that there may be certain elements which in biological condition are difficult to stabilize, but if nature decides to use that particular element, then that particular element must be able to serve multiple purposes. And the most celebrated example here is iron. Since we don't have time, we cannot go into details, but I have told you that the ferric iron particularly has got very low solubility at biological pH. So but we know we cannot survive without iron, without ferric iron, etc. And so nature has to spend a lot of effort. It has to design a lot of different pathway to so that iron is stabilized in our body. And so in return for this extraordinary effort to stabilize iron in biological system, what nature gets in return, our biology gets in return. In return, it gets the fact that iron is the only one metallic ion which has got so many different functionality. So multiple functionality is a very important criteria for choosing certain difficultly soluble elements, and iron satisfied that condition. So before going further, if you have any questions so far regarding essential, because we have finished the part of essential more or less, except one or two slides. If you have any question in this part, you may ask. No. Now, here, next two or three slides, it may be somewhat boring to you, and whatever is presented here, you may not have to remember all those things, because these things, many of these things you have to remember rather than uh, understand, or understanding will be difficult. So here, but you may not be required to, I mean, remember all the these defined amounts. Only the relative amount you can remember. So here in this table, what we have said, or what we have shown here, is the all metal. So biologically important metal ions, essential metal ions. What are their functions, right? And in what amount they are present in a human body. So part 70. So standard, because it is a Western standard mainly. So a standard human being is considered to have 75 kg of body weight, and so part 75 kg of body weight. What is the amount that is present that is presented here? So, first of all, you like to look at sodium and potassium. They mainly act as charge carrier in our body and maintain osmotic balance. And as I have told you, they are bulk essential elements, so they are present in several hundreds of grams in our body, right? Sodium, potassium are present several hundreds of grams, and you notice that potassium is required more in our body than sodium. And again, this is a subject beyond our discussion, but you please notice that if you look at the natural abundance of sodium and potassium, then you will find that so natural abundance of sodium is more than that of potassium. But biology demands, or living system demands, at least human body demands more of potassium than sodium. So nature has to devise special way to pump in more potassium and throw away extra sodium. Then we have calcium and magnesium, the alkaline earth metal ions. They are also present in grams quantity, and you can easily see that among all the elements, among all the metal ions, calcium is present in largest quantity. It is 1.1 kg part 75 kg of body weight, and this is because it constitutes the skeletal and bone, right? So obviously it will have much larger amount. So calcium plays the structural role, particularly the bone structure, right? And the skeletal structure. And the calcium also is also called a second messenger, in the sense that it also functions as for certain trigger mechanism for muscle contraction, etc. So it actually transduces certain nerve signals, and it induces muscle contraction. And so nerve signal transduction and charge transfer, fertilization, etc. So calcium has got immensely important role, and that's why deficiency of calcium leads to a lot of problem, right? Magnesium again is involved in muscle contraction. So along calcium triggers muscle contraction, whereas the muscle contraction movement actually is to some extent controlled by magnesium. And then again, magnesium also has also got certain function is nerve signal regulation. Magnesium is very important for hydrolytic enzyme, hydrolase and isomerase, particularly ATP to when ATP hydrolyzes to ADP and phosphate, and energy is released. That hydrolysis, so ATPase, where ATP is hydrolyzed to ADP and energy is released, Sorry, that hydrolysis reaction is catalyzed by magnesium ion. So very important role of magnesium in hydrolysis reaction, isomerase reaction. And apart from the role in human being or vertebrates, magnesium is very important part of the chlorophyll, right? So which actually collects the sunlight and then uses it for chemical energy. Vanadium, again, it is a trace essential, or even you can call it ultra trace essential metal ion. Vanadium, you can see it is present in milligram quantity, unlike the previous four metal ions, which are present in gram quantity. So, vanadium is present in milligram quantity, and vanadium has got role in it is glucose metabolism and certain oxidase reactions. Beside, in plants and certain bacteria, it has got role in nitrogen fixation. So in vertebrates and mammalians, it has got role in oxidase and glucose metabolism, and in plants and certain microbes, it has got role in nitrogen fixation. So just one minute. Then chromium, I have told you that chromium role is still under debate. Some people call it essential. Some people call it beneficial. So depending on the book or depending on the scientist, they will find divergent view. So chromium has got. It is now established that chromium has got a role in glucose tolerance. Right? Chromium breaks down fats and carbohydrates. So role of chromium in breaking down carbohydrate is important, and it also stimulates fatty acid and cholesterol synthesis. So chromium nowadays has been clearly established that chromium has got function in glucose metabolism, right? Particularly breaking down of carbohydrates. And there are some people who believe that it also plays important role in actually metabolism of fats, right? And in fact, in certain Western countries, certain chocolates are sold called chromium picolinate chocolates. The chemical constituent is chromium, and it is coordinated to pyridine to carboxylic acid. So chromium picolinate tablets, and some people believe that these chromium tablets help in dissolving excess fat, but it is questionable whether it is really capable of doing so much things. So it is present in only 2 milligram quantity. Then manganese, again, it is present in very small amount, 1 gram per 75 kg, but it has got very important role, particularly in our mitochondria, because mitochondria is our powerhouse, right, in cells. So in mitochondria, there is continuous metabolism is taking place, and that's why where oxygen is being consumed, and sometimes oxygen is incompletely reduced to superoxide, and that superoxide in mitochondria is being disproportionated using an enzyme what is called superoxide dismutase, which is a manganese enzyme. So manganese has got very important role in safeguarding us from the deleterious effect of superoxide. Besides this, it has got certain other oxidase role, right? That is certain oxidation reactions. And in photosynthesis of plants, I have told you there is a tetranuclear manganese complex which is responsible for the evolution of oxygen or oxidation of water to dioxygen that is carried out by manganese complex. Clase aji, clase. Then molybdenum, there again it is present in very small quantity, 10 milligram, and molybdenum has got very important role in oxidase and oxotransfer reaction. Now some of you may ask me, sir, what is oxidase reaction? Now you see, when you have redox reactions are catalyzed or characterized in various ways depending on the or various headings depending on the nature of the redox reaction. Some redox reactions are clean electron transfer reaction, that is only electron transfer is occurring, no other atom transfer is occurring. So that they are called simple electron transfer reaction, redox reaction, but simple electron transfer reaction. But in some redox reactions, along with electron transfer, certain atom transfer like hydrogen atom transfer or oxygen atom transfer may take place. Now one kind of redox reaction is called oxidase, whereby electron transfer is taking place, but ultimate electron acceptor is oxygen. So any redox reaction where ultimately the electron sink is dioxygen, which is converted to water or hydroxide or oxide, that will be called the oxidase reaction. So oxidase means electron transfer reaction, redox reaction, where ultimate electron acceptors are the dioxygen, which is being converted to mainly water or oxide ion, right? Oxotransfer reaction means one oxygen atom is transferred from one atom to the another, one metal ion to the another metal ion, or one metal ion to another non-metal ion, etc. So oxotransfer reaction, and also in plants, molybdenum is involved in nitrogen fixation. Then if we go to iron, it is all of you know it is involved in dioxygen transport, myoglobin and hemoglobin in our body, and also there is certain other lower animals. It has got hemerythrin, another oxygen transport protein, and lots of oxidase reaction, electron transport reaction, and nitrogen fixation reaction. And you can see, as I have told you previously, that among all the transition elements, iron is required in the largest quantity, 4 to 5 gram per 75 kg of the body weight. Then if you go to cobalt, cobalt is required in very small quantity, 1.2 gram per 75, 1.2 milligram per 75 kg. And cobalt has got, here it is written isomerase and alkyl group transfer reaction, but you must know that cobalt, vitamin B12 particularly, or coenzyme B12 plays a very important role in synthesis of porphyrins, which actually are constituent of the hemoglobin. That is the heme part is being synthesized using the catalysis of cobalt. So without cobalt, your blood formation is inhibited. So that's why cobalt is very important, though it is present in very small amount. Nickel, again, if there are certain hydrolytic enzyme like say urease enzyme, which hydrolyzes urea to ammonia, right? That kind of enzyme, and certain hydrogenase reaction. Just as oxidase means oxygen is reduced, in hydrogenase actually what happens, in hydrogenase, a hydrogen ion is reduced to hydrogen, or the reverse reaction, hydrogen gas is converted to hydrogen ion. So there nickel is involved. Then copper, again, if you consider in terms of the amount, relative amount, then next to iron, the most important transition element is copper, which is present in 80 to 120 milligram, 80 to 120 milligram per gram per 75 kg. And copper again plays multiple oxidase functionality in our body, electron transfer reaction, dioxygen transport, etc. Dioxygen transport not in our body, but in certain invertebrates, like say a certain kind of fish, right? So dioxygen transport, it plays very important role. Whereas for certain kind of spiders, etc., or dioxygen transport in octopus, etc., that are actually carried out by certain these copper enzymes, right, or copper proteins. And zinc, again, it has got structural role and functional role. Structural role and certain hydrolytic enzyme. Most of the hydrolytic enzymes are zinc enzyme. And I have told you, zinc has got tremendous structural role in our body in stabilizing the enzyme structure, protein structure, even membrane structure, etc. And again, zinc is also present in large amount. So these are some of the metallic elements and their function. What you must know, you may not remember the exact amount, or you need not remember the exact amount, but you must know that between so among the metal ions, most amount is of calcium. Next you have sodium and potassium. Between sodium and potassium is required more than sodium, right? And among the transition metals, most important or in terms of amount is your iron, and then copper, and to some extent zinc also. The zinc is not strictly a transition metal. And you must remember this part, I cannot help, you have to remember certain functions of this metal ions, right, in our body. Then the next slide, so this slide actually tables, here we actually show that deficiency symptoms in human, when these metal ions or some non-metals are there, when they are absent or they are not absent, because if they are absent, they are essential, the life system will stop. If they are deficient, then what are the likely deficient symptoms? This is not a comprehensive list of symptoms, but some of the salient symptoms that you may get. So you can easily imagine that if there is a calcium deficiency, there will be retarded skeletal growth that you can expect. Since magnesium is involved in muscle contraction, so in absence of magnesium, or rather when there is magnesium deficiency, there will be muscle cramps, right? But doesn't mean muscle cramps always indicate magnesium deficiency. But if you have magnesium deficiency, there is possibility of getting muscle cramps. If you have sodium deficiency, you have reduced blood pressure and what is called Addison's disease. In Addison's disease, your adrenaline is not being properly synthesized, and as a result of this, you have multiple symptoms of low blood pressure and other kind of symptoms, palpitation, etc., etc. So Addison's disease refers to reduced amount of synthesis of your adrenaline. Then you have iron deficiency. All of you know iron deficiency leads to anemia. Not only that, since iron is, I am repeatedly telling, iron is one metal ion which is involved in multiple very important enzymes in our body. So absence of iron also leads to disorder of immune system, right? Or rather, not absence, the deficiency of iron leads to disorder of immune system. Then zinc, deficiency of zinc leads to skin damage, because the membrane structure of the skin to some extent is held by the zinc ion. Then zinc has got multiple, again, there are multiple zinc enzymes in our body, very important enzymes. And when you have a zinc deficiency symptom, that may lead to stunted growth or so-called dwarfism. That means you understand what is meant by dwarfism. The size remains, even if the age increases, the size doesn't increase. And then you have the endocrinal deficiency in boys. So in boys, if you have zinc deficiency, then you may have endocrinal hormonal deficiency in boys. For copper deficiency, very interesting. Copper deficiency leads to artery weakness, liver disorder. There is one disease called Menkes disease. It is found generally in the newborn babies, right, where due to certain genetic disorder, their copper handling mechanism is not well developed, and generally this kind of babies die within 2 to 3 years, right? But very interesting, here we have listed one anemia called secondary anemia. And so it happens so that even if your body contains sufficient amount of iron, but you may show symptoms of anemia if two other metal ions are absent or two other metal ions are deficient. What are these metal ions? One is the copper ion and other is the cobalt. So even if you have sufficient iron, if your body is deficient of either copper or cobalt, then you may get symptoms of anemia. Now, when you have a copper deficiency that is leading to anemia, it is called secondary anemia. Now, why it is so? Why copper copper deficiency leads to anemic symptom? This is because in our body, iron is present mainly in the +3 and +2 state, though during certain enzymatic process, it may go to +4 and +5 state also. But mainly it is +2 and +3 state. Now, between +2 and +3 state of iron, Plus 2 state is very much labile. It is that means it is kinetically it reacts very fast. Whereas normally ferric iron, it is kinetically a slow reactant. So what happens that when suppose a iron enzyme is being constituted by reacting the protein part and the metal part. So what will happen that initially iron is inserted inside the enzyme as a ferrous iron because ferrous reacts faster. So if you react with the ferrous iron, the metallic enzyme will be constituted very fast. On the other hand, if it reacts with ferric, it may be that constitution will require more time. So because ferrous is more labile, more reactive, so when the enzyme is constituted from the protein and the metal ion, it is in the ferrous form. But once the enzyme is formed with the iron inserted inside the enzyme, your enzyme for its function required to be converted to the ferric form. And this ferrous to ferric oxidation, sometimes it is called ferro-oxidase reaction. That means ferrous is being oxidized to the ferric form. Hello? Hello? আপনি আমার ইয়েতে দিয়ে দিন কেয়ারটেকার দিয়ে দিন না ঠিক আছে এই নিউ টাউন দেখুন না এটা আমি ক্লাসে আছি পরে কথা বলুন ঠিক আছে নিউ টাউনে আমার অ্যাড্রেস দেওয়া আছে দেখুন ঠিক আছে ও বি কলেজ ফার্স্ট গেট তাহলে কেমিস্ট্রি ডিপার্টমেন্টে চলে আসুন কেমিস্ট্রি ডিপার্টমেন্টে চলে আসুন কেমিস্ট্রি ডিপার্টমেন্ট So what happens that it is a copper enzyme called ceruloplasmin which is responsible for the oxidation of ferrous to ferric. So if your body is deficient of copper, what will happen that even if iron is inserted in your enzyme, it will not be oxidized from ferrous to ferric, and if it is not oxidized from ferrous to ferric, then proper functioning of the enzyme or protein is inhibited, and so your body will not will show symptoms of iron deficiency. So copper deficiency leads to symptoms of iron deficiency because in absence of copper or in presence when copper is in deficient amount, then oxidation of ferrous iron to ferric iron in enzymes is inhibited, and that actually creates a situation as if there is iron deficiency. Then we have manganese, where manganese deficiency again leads to infertility and retarded skeletal growth, right? Cobalt deficiency, I have told you, cobalt deficiency may also lead to anemia, and previously those anemia which were due to cobalt deficiency, they cannot be treated because in the early part of the 21st century or the end of the 20th century, the cobalt vitamin B12 was not synthetically available, right? It was not identified, and as a result of this, people who have some deficiency in their body of absorption of vitamin B12, natural vitamin B12, they showed they showed the deficiency of iron, anemic tendency, and ultimately they die. They could not be treated. But nowadays we have synthetic way to prepare vitamin B12, and that's why this kind of anemia which is coming from the deficiency of cobalt can be easily treated by feeding the patient with the vitamin B12 capsules. Then nickel deficiency again lead to dermatitis, that means certain skin problem, and growth depression. Chromium deficiency, since chromium is involved in the metabolism of glucose, so chromium deficiency may lead to diabetic symptoms. Silicon deficiency, because calcium silicate is also important part of the skeletal structure, so silicon deficiency may lead to disorder of skeletal growth. All of you know fluoride deficiency leads to dental caries. That means the dental structure is to some extent degraded, right? Iodine deficiency, again, it is a common knowledge, it leads to thyroid disorder and retarded metabolism. And silicon deficiency leads to muscular weakness, particularly the cardiac muscles is severely affected, and that's why it is called cardiomyopathy, meaning that the cardiac muscles are weakened. So this is your deficiency symptoms. In the next slide, we have the reverse thing. That means what happens? We have excess of certain essential metal ions, because as we have learned that excess of essential metal ions also leads to toxicity, right? So excess of beyond certain optimal concentration, if you have excess of any essential element, that also leads to toxicity. Sodium excess, that will lead to high blood pressure called hypernatremia, right? Potassium deficiency. So excess, sodium excess will lead to high blood pressure. Potassium excess will lead to excretion of sodium, right? And so it will lead to Addison's disease. So it will show sodium deficiency symptom, and so it will show Addison's disease and certain cardiac failure. All of you know that for proper function of the cardiac system, we have a proper sodium potassium balance, right? So potassium excess may lead to also cardiac failure. Calcium excess, calcium, what happens? Calcium in our body, if it is present in excess, uncontrolled intake of calcium, what will happen in our body? There are there are carbonates, there are oxalates that are produced in our body, and if you have excess calcium, that calcium may react with the carbonate, oxalate, sulfate, etc. Ion in our body to form insoluble precipitates of calcium sulfate, calcium oxalate, calcium carbonate, and those precipitates may lead to cataract and stones in gallbladder, kidney, etc. So calcium, uncontrolled intake of calcium. Some people take calcium tablets very often, but uncontrolled intake of calcium tablet is not recommended. In fact, uncontrolled intake of any metal ion is not recommended. So if you have calcium excess, it may lead to stones, particularly, and cataract. So cataract and stones in parts of the body like gallbladder and kidney may be developed. Now, if you have iron excess, that is also not very good for body. Iron excess lead to certain blood disease called hemochromatosis, and also lead to certain liver damage, right? Copper excess, it leads to a symptom, again very famous disease called Wilson's disease. In the Wilson's disease, what happens? Again, due to certain those people who have Wilson's disease, they have certain genetic problem leading to deficiency of the synthesis of ceruloplasmin enzyme or ceruloplasmin protein, and that ceruloplasmin is responsible for the homeostatic balance of copper in our body. And so if you have copper deficiency, then what will happen? Then there will be deposition of copper in various parts of the body, particularly in liver, in brain, in even in retina, right? And excess copper deficiency, excess copper actually, sorry, excess copper. You have excess copper, then there will be liver damage, then there will be Wilson's disease, which actually leads to, or which actually pertains to deposition of copper in brain, that is neurological function is affected. And if it is so much excess of copper, then sometimes there may be green or blue ring around the retina, right? So that means you have uncontrolled deposition of copper in our body, and that is happening because of the deficiency of ceruloplasmin in your body. Now, cobalt excess may lead to coronary failure, and zinc excess may lead to certain kind of disease called metal fume fever, which actually affects those people who work in zinc mines, right? So metal fume disease. Just one minute. কিছু করতে হবে না স্যার, ওটা তো দেখে নিন, ওটা ঠিক আছে কিনা। সই করার কিছু নেই স্যার, সই করে দিন না, ঠিক আছে। So this completes our discussion on the essential elements, right? So this part is complete. So we have discussed what are essential elements, so what are their homeostatic mechanism, what are the factors that determine essentiality, etc., etc., right? And then we shall move to another very important topic from where very often questions come called chelation therapy. Now, starting chelation therapy, I must ask you that whether you know what is chelate effect. Anyone?
Sir, ring effect, ring formation will occur.
What happens then?
Sir, stability occurs due to the ring formation.
Okay, okay. So roughly it is true. So it means uh, chelation effect or chelate effect means that when you have certain ligands which has got multiple donor atoms, then it will have those kind of complexes with those kind of donors has got more stability than say monorented ligand. So here we have shown that suppose we have a copper metal ion and we know it can react with four ammonia molecules to form cupamine complex. And let us say we measure its stability constant, it is K. Now, compared to this stability constant of copper ion with the ammonia, if we consider a copper complex of say ethylene diamine, say two ethylene diamine molecules are coordinated to copper like this, like so CuN2 2 plus. We'll find that though in terms of donation, here we have four ammonia which are donating to copper in a square function. Here also four amine ligands which are very closely allied with the ammonia, derived from ammonia we can say. So here also four amine nitrogens are coordinated in a square planar fashion around copper. But invariably we shall find that this তপন আমি ক্লাসে আছি একটু পরে কথা বলছি So invariably we shall find that this cupric ethylene diamine complex will have more stability than the cupamine complex. Or if I take even more, I mean more denticity of the chelating ligand, like say here we have diethylene triamine, right? So two ethylene groups are there and there are three amines. So if I consider a reaction of diethylene triamine with copper, then diethylene triamine complex will have more stability. Now, the reason for this extra stability of the chelate complexes lies in the fact that stability constant is related to the Gibbs free energy by the relationship delta G equal to minus RTLN K. So if delta G becomes negative, K becomes more positive. That means you have the higher stability. So higher stability means higher K value and means more negative delta G. Now delta G, this free energy has got two components. One is called the enthalpy component, and the other is called the entropy component. And you can see easily they have got different signs. Enthalpy component has got a positive sign, whereas entropy component has got a negative sign. Now, the reason why chelated complexes are more stable, that means their delta G is more negative, is due to the fact that for both the complexes, since the donor type is same, so delta H is very similar. Delta H does not change much on going from a monorented ligand to a multirented ligand. But what changes much is the entropy factor. When you have a chelated complex, then delta S is more positive, and if delta S is more positive, since it is preceded by a negative sign, so delta G becomes more negative, and so your delta G becomes more negative means the stability constant becomes more positive. So the driving force for the chelation effect is mainly the entropy factor. And why the entropy factor is coming? Again, look at these two reactions. So if you look at the formation of the cupamine complex here, what you find that in the left hand side we have started with 5 species, that means reactant we have got 5 molecules, and in the product side we have also 5 molecules. So number of molecules or number of species do not change much. So in terms of entropy, at least for at least this number of species, the entropy is governed by many factors. It has got the number of species, that means the translational entropy, the rotational entropy, the vibrational entropy, etc., etc. At least in terms of translational entropy, since the number of species remain identical, so entropies, that kind of entropy do not change. On the other hand, if you take the formation of the ethylene diamine complex, what do you find? That the left hand side, in the reactant side, we have 3 species, but in the product side, we have 5 species. So number of species changes, number of species increases, and number of species increases means there is more. If the number of species increases, just as in a classroom, if number of students increases, there is more chaos. Similarly, if number of species increases, there will be more chaos. So, and that leads to increase of the entropy, right? So, increase of entropy takes place, and entropy increase means the delta G becomes more negative, and so your stability constant will increase. So, the main reason for the chelate effect is in case for when we have a chelate complex formation, the entropy increases much, and there is the other factor which is called the statistical factor. By statistical factor we mean here that suppose we have a cupamine complex. Now suppose it is a dynamic process, we know. So in presence of say water, which is a solvent, what happens? Sometimes some of the ammonia molecules are going out and water is coming in. So there is a reversible reaction that is occurring. Now when you have a monodentate ligand, then once the ammonia goes out of the coordinate sphere, it is lost in the solvent atmosphere, and so in order to form this cupamine complex, tetracupamine complex, again it has to fight with other solvents to come near the coordinate sphere and be coordinated with the copper. And so ammonia, once it goes out of the coordinate sphere, it has to fight back with other solvent molecules. On the other hand, when you have a ethylene diamine complex like this, so suppose one nitrogen end is loosened up and the water is coordinated, as just I have shown here. But since it is a chelated ligand, the other nitrogen end is still coordinated to copper. As a result of this nitrogen is actually not lost in the solvent jungle, but rather it remains dangling near the coordinate sphere so that it can easily fight back and replace the water. So in terms of statistical factor, so there is more probability that the chelate complex becoming more stable than the non-chelated complex, because for non-chelated complex, the ligand, once it is dissociated, it has to fight back with the other solvent molecules for reforming the complex, whereas in case of chelate complex, because of the chelate effect, the dissociated ligand remain dangling around the coordinate sphere, and it can easily come back and replace the solvent molecule. So this leads to so this is in short what is called chelate effect. Now this chelate effect is used for the treatment of metal excess or metal poisoning, right? Metal poisoning. Now question is, I shall discuss this chelation therapy in detail later, but for the time being, first of all, let us try to find out what are the factors. This is very important, and from the examination point of view also very often this question is asked, that if I want to choose a chelating agent for chelation therapy for removal of toxicity due to a metal ion, it may be a toxic metal ion or it may be an essential metal ion which is present in large excess and that is creating toxicity. So what are the factors that will prompt us to choose a particular chelating agent? And here we have I have actually listed 4 factors. First of all, the chelating agent must have high affinity towards targeted metal ion. That means chelating agent must be able to form very stable complex with the targeted metal ion, and its binding constant for the targeted metal ion should be sufficiently higher than that of the biological species to which the metal ion is bonded. That means suppose a metal ion is developing toxicity in our body. Why it is developing toxicity? Probably it has bound to certain essential protein or enzyme, and that is blocking the function of the enzyme. So there is certain biological ligands which has already chelated that particular metal ion, the toxic metal ion. Now, if you want your chelating agent to remove the toxicity, what your chelating agent needs to do is it needs to fight with the biological ligand, and it needs to win. And it needs to win the battle. That means it needs to snatch the metal ion from the biological ligand so that it can complex it and it can throw it away outside the throw it outside the body. So the main thing is that the binding constant of the metal ion for the chelating ligand must be much higher compared to the binding constant of the metal or of the toxic metal ion with the biological ligand. So first thing is that the chelating ligand which you are choosing for chelation therapy must have very high affinity towards your targeted metal ion, and this affinity or this binding constant should be higher than that of the biological ligand to which the metal ion is bound. Okay, understood for the first point. Second point is that it must show high specificity towards targeted metal ion. So that means if I want to say treat a patient with lead toxicity, then ideally our chelating agent should be such that it will go inside the body, pick up the lead ion only, but it will not affect say other metal ions like say calcium or zinc, etc. So it must have high specificity towards the targeted metal ion. That means our chelating agent ideally should be such that it should go inside the body, pick up the targeted metal ion only, but it will not target any other essential metal ion. But this is a very ideal situation and very difficult to achieve that. But we have certain chemical principles to understand what kind of ligand design is needed for this kind of chelation therapy. And one very important principle which actually determines how to design such specific or targeted therapy is called HAB, Hartsoft acid-base principle. Now, have you got any exposure to Hartsoft acid-base principle? Anyone? Have you heard about the Hartsoft acid-base principle?
No, sir.
No. So I shall quickly, very quickly, I shall go to the Hartsoft acid-base principle. It is nothing very extraordinary. Hartsoft acid-base principle. So first of all, what do you mean by a hard acid or hard base, and soft acid and soft base? What this hardness and softness means? Now, this hard word is coming from the fact that those acids or bases which whose electron cloud is hard to deform or hard to polarize, they are called hard acids or hard bases. So what are hard acids or hard bases? Those acids or bases which held their electron cloud very firmly, so that it will be difficult to deform those electron clouds. It will be difficult to polarize those electron clouds. Those acids or those bases will be called hard acids or hard bases. On the other hand, soft acid or soft base will be those kind of acids or bases where the electron cloud is not held very firmly, so that in the presence of certain field, is a electric field, or in the presence of certain polarizing species, it will be easier to polarize those electron clouds. It will be easier to deform those electron clouds. So that's why they are called soft acid or soft base. That means they are soft with respect to polarization, soft with respect to deform. So hard means hard to deform the electron cloud, soft means soft to deform the electron cloud. Now, from the common sense, What kind of acids will be hard? Acids, metal ions are generally acids. Cations are generally acid because they are electron deficient. And from the Lewis acid base criteria, those who are electron deficient, they can accept a pair of electron to make up for the electron deficiency. So generally cations behave as acids, and generally anions behave as base because anions are with excess of electrons, so they can donate a pair of electrons if they are Lewis base, and generally cations are acids. So when cations will be difficult to polarize, obviously if a cation has got small size and high positive charge, right, when a cation has got small size and high positive charge, then it will hold its electron cloud very firmly, and so those will be the hard acids. So hard acids refers to those metal ions which has got high positive charge and smaller size. For instance, if we compare between chromium 3 and chromium 6, though chromium 3 itself is a hard, but between chromium 3 and chromium 6 will be a harder acid because it has got more positive charge, and it has got smaller size. Similarly, between ferrous and ferric 3 will be a harder acid than ferrous because ferric has got higher positive charge and smaller size. Between arsenic 3 and arsenic 5, again arsenic 5 will be harder acid and arsenic 3 will be relatively softer because arsenic 5 has got higher positive charge and the smaller size. So any cation with high positive charge and smaller size will function as hard acids. On the other hand, what are hard bases? Hard bases obviously means they are anions. So if there are anions, obviously now they have
Sir,
got, yes.
sir, can you please stop now because we have maths test from 3:30.
Oh, 320, yes. I will stop here. Okay, thank you very much. Okay. So, okay. Thank you for reminding me.
Thank you,
So I'll stop it here. Okay.
Thank you, sir.
Okay, sir.
Thank you, sir. Okay.
Thank you, sir.
Mhm.
Thank you, sir.
Thank you.